Algorithm Design and Analysis course. In this session, we focus on how to find the computing time of Strassen matrix multiplication. Previously, we have discussed how to devise the Strassen matrix multiplication algorithm, and we have verified the intermediate calculations and final computations, CAJ computations, according to Strassen. In this session, we focus on how the computing time of Strassen matrix multiplication is obtained and how we are going to solve the recurrence relation that we have obtained earlier. Assuming a T of n represents the computing time of n by n matrices multiplication, then T of n, this is obtained by applying the Strassen equations as we computed earlier. The intermediate calculations P, Q, R, S, T, U and V. These are used to find the main computations CIJs, that is C11, C12, C21 and C22. Suppose a T of n is the computing time to represent 2 n by n matrices multiplication A and B, right? A is of order n by n, B is of order n by n. Then, according to Strassen, we are going to apply the divide and conquer logic recursively until the input matrix reduces the size 2 by 2. So, initial size is n by n. Initial size is n by n. Assuming that n is represented in the form of 2 power k, k greater than 0, k is an integer. When n is not represented in the form of 2 power k, then we need to add enough number of dummy rows and dummy columns to make the matrix into this n by n format. So capital A is of n by n, capital B is of order n by n. Then the resultant matrix is also of order n by n. Initial matrix is of order n by n. This n by n is subdivided by 2, n by 2 by n by 2 in the first recursion. Then in the next stage, this n by 2 by n by 2 is subdivided by 2, so that we will get n by 2 power 2 into n by 2 power 2. Then this is subdivided by 2 in the next recursive call as n by 2 power 3 into n by 2 power 3. So in each recursive call, the matrix size is subdivided by 2. In the final stage, when the input matrix becomes this order n by 2 power k into n by 2 power k, where n is equal to this 2 power k, so that n by 2 power k becomes 1 by 1. So when the input size becomes 1 by 1, as we discussed earlier in the conventional matrix multiplication, capital A is a matrix of order 1 by 1. Suppose A11, only one element. And capital B is of order, right, 1 by 1, having only one element. What is A11? Only one element, right, first row, first column. B11, only one element, first row, first column. This stage, the resultant matrix C11 is obtained directly multiplying the values A11 and B11. So how long we are continuing the recursion until the input size, that is greater than or equal to. When the input size n becomes 1, that stage we need to terminate a recursion. When n reaches 1, terminate a recursion. For n greater than or equal to 2, apply the divide and conquer logic. So apply recursively the computations of CIJs using the intermediate calculators P, Q, R, S, T, U and V. Hence, A is of order n by n, B is of order n by n. This stage, the computational time for finding C is equal to n by n. This is represented using the notation T of n. So that's what we have. T of n as the computational time. T of n, this is equal to 7 into T of n by 2 plus A into n square. This is true when n is greater than or equal to 2. 7 multiplications are required for the matrices of orders n by 2 by n by 2. Then we need to add the matrices. N by n matrices are added using theta of n square computational complexity, as we have discussed in the conventional matrix multiplication. That's what here we have added the quantity A into n square with 7 into T of n by 2. So here T of n is equal to 7 into T of n by 2 plus A n square. This is true when n is greater than or equal to 2. Otherwise, we have a constant computational time C when n is less than 2 or simply when n is equal to 1. When n is equal to 1, we need to consider this as the termination condition. This is a recursive condition. So let us call this is equation 1 and this is equation 2. Equation 1 is a recurrence relation. Equation 1 is a recurrence relation where equation 2 is the termination condition. Termination condition. Let us solve this recurrence relation by applying the substitution method. Solving this recurrence relation using the substitution method. As we have solved earlier the conventional matrix multiplication using the substitution method. Here 7 into T of n by 2 plus A n square is there. Let's apply the substitution method. So writing here a T of n. T of n is T of n. T of n is 7 into T of n by 2 plus A into n square. This is true for n is greater than or equal to 2. Now we are going to find the value T of n by 2 from equation 1. So what is equation 1? T of n is equal to 7 into T of n by 2 plus A n square. If you put n is equal to n by 2, this implies T of n by 2 is equal to 7 into T of n by 2 by 2. Let's write n by 2 for 2 plus A into n by 2 the whole square. So T of n by 2, this is substituted using this equation 7 into t of n by 2 power 2 plus a into n by 2 whole power 2. So writing here 7 into t of n by 2 is 7 into t of n by 2 power 2 plus a into n by 2 the whole square plus a n square. Since substitute n is equal to n by 2 in equation 1, t of n by 2 is obtained. Now t of n by 2 is obtained. We need to simplify this equation one step further. 7 into 7, let's write as 7 square into t of n divided by 2 power 2 plus this is written as 7 by 4 into a n square, because a into n by 2 whole square, that is a into n square by 4, that becomes 7 by 4 a n square plus the term a n square is written as it is plus a into n square. Now extending the recurrence relation one more stage so that we can find the value of t of n by 2 power 2. T of n by 2 power 2. This is obtained by putting n is equal to n by 2 power 2 in the first equation. So let's find t of n by 2 power 2 first. Then let's substitute in this place to have the extension for the next stage. T of n is already we defined. T of n is 7 into t of n by 2 plus a into n square. Now substitute n is equal to this one, n by 2 power 2. Substitute n is equal to n by 2 power 2. Put n is equal to n by 2 power 2. Therefore, t of n by 2 power 2 is equal to 7 into t of n by 2. If it is n, n is halved n by 2. So n by 2 power 2, n by 2 power 2 by 2, it becomes n by 2 power 3 plus a into n square, that is n by 2 power 2 the whole square. Just n is replaced by n by 2 power 2, that is n by 4 actually. So you will get a into n by 4 the whole square. Now this result is being substituted into the law of equation in which t of n by 2 power 2, this is substituted. So substituting this value here, t of n by 2 power 2, using that equation, left hand side is t of n. So we write as t of n is equal to, this is equal to 7 square into t of n by 2 power 2, right? This is actually that replacement, t of n by 2 power 2. So replacing this right hand side here, this is 7 square into 7 into t of n divided by 2 power 3 plus a by 4, right? A 4, right? We can write as a 4 square. Then 2 power 2 4, 4 square. N square, right? The term is written n square, or we can write as n by 4 the whole square, 2t, plus the replacement has been done for t of n by 2 power 2. What about remaining two terms? This will be written as it is 7 by 4 a n square plus a n square. So plus write 7 by 4 a n square plus a n square. These two terms are written as it is. Now simplifying this recurrence relation, right, one stage further, let's multiply these terms with 7 square. We have 7 square into 7, 7 power 3 into t of n divided by 2 power 3 plus 7 square by 4 square. Let's write this as 7 by 4 the whole square multiplied with a n square plus 7 by 4 multiplied with a n square plus a n square. This is a simplification in this stage. Now we need to simplify the right hand side. To simplify the right hand side, let's find the generalization. Initially 7 power 1 into t of n by 2 power 1, right? Here have a look into 7 power 1. This is t of n by 2 power 1. Next stage here 7 square into t of n by 2 power 2. After extending the recursion one more stage, we have 7 power 3. This is 7 power 3 into t of n by 2 power 3. As we discussed earlier, here we have this is n by 2, n by 2 power 2, n by 2 power 3. So final stage that should be n by 2 power k, right? Then only t of 1, right? That results in a constant computational time. There recursion terminates. So writing now the generalization, right, etc. In the final stage, this is 7 power k into t of n divided by 2 power k plus. We need to find the rest of the terms. So to find the rest of the terms, here 7 power 3, 7 power 3, 2 power 3. This is 3 means here, this is 3 minus 1, so 2. Here when we have 7 power 2, 7 power 2, the power of 7 by 4 whole, 7 by 4 is, right, 1. That is 2 minus 1. Likewise here 7 power 1, here we have the term, right, that is 7 by 4 whole power 0, right, that is 7 by 4 whole power 0 is 1, 1 into a n square, a n square. So the generalization is, having here this power is 3, the next term is 7 by 4 whole square into a n square. Likewise, if the power is k here, the next term is 7 by 4 whole power k minus 1 into a n square. Then next term becomes 7 by 4 whole power k minus 2 into a n square plus etc. plus the last 3 terms are, say, 7 by 4 whole square into a n square plus 7 by 4 into a n square plus a n square. This is a generalization. This is inferred, right, by extending the relations, recurrence relations, right? This way n by 2 power 1 into n by 2 power 1, n by 2 power 2 into n by 2 power 2, n by 2 power 3 into n by 2 power 3. Then in the final stage, that will be n by 2 power k into n by 2 power k. So that's what here in the final stage we have the recurrence relation written as 7 power k into t of n by 2 power k. Now since n and 2 power k are equal, n is equal to 2 power k, so that t of n by 2 power k becomes t of 1. That means the actual parameter becomes 1. So that recursion terminates. So writing in the next stage, replacing n is equal to 2 power k, t of n is equal to t of n is equal to 7 power k into 7 power k into t of n by 2 power k. Since n is equal to 2 power k, n by 2 power k becomes 1. Then plus remaining terms need to be simplified. So from these 7 by 4 whole power k minus 1 into an square, 7 by 4 whole power k minus 2 into an square, 7 by 4 whole square into an square, 7 by 4 into an square plus an square. It seems all these terms have a common factor of an square. As we solved earlier in the solution of conventional matrix or divide and conquer based recurrence relation, here we can take a common factor an square. So commonly taking an square, the rest of the terms are, let's write from right to left, an square into 1 plus right to left direction, an square is taken, so the term is 1 plus, then 7 by 4 into an square, here an square is taken, so we will get the term, right, 7 by 4, 1 plus 7 by 4, 1 plus 7 by 4 plus the next term, that is the third term from the rows, an square is taken, next the factor is 7 by 4 whole power 2, so writing here 7 by 4 whole power 2 plus etc. plus the last term is this one, 7 by 4 whole power k minus 1, 7 by 4 whole power k minus 1, since n is equal to 2 power k. Now we can replace, right, t of 1 as a termination condition. When n is equal to 1, actual parameter is 1. That is t of 1. This results in C, a fixed number of operations. Now replace t of 1 is equal to C here. Writing a t of 1 as C, we can represent here, this is 7 power k, this is equal to 7 power k. Now also, right, we can replace the value of k as log n base 2. Since n is equal to 2 power k, taking log to both sides, we have log n base 2 is equal to log base 2 power k. This is equal to k into log 2 base 2, that is k. So clearly the value of k is log n base 2. So replacing here, this is k as log n base 2, 7 power log n base 2 into t of 1. T of 1 is C. When the actual parameter n becomes 1, then the input size n becomes 1. We need to have a fixed amount of operations, that is C. T of 1 is equal to C, right? Since from a 2 also, from a 2, T of 1 is equal to, since from a 2, T of 1 is equal to C, that is written here. A plus an square, this is in the form of a geometric series. We know the geometric series 1 plus x square plus etc. plus x power n is equal to Assuming x is greater than 1, absolute value of x, the common ratio, this is greater than 1, we have x power n plus 1 minus 1 divided by x minus 1. So the relationship between this geometric series to our expression 1 plus 7 by 4 plus 7 by 4 whole square plus etc. 7 by 4 whole power k minus 1. That k minus 1, that is equal to a value n. So the relationship is n is equal to k minus 1. And what is x? X is 7 by 4. So replacing this geometric series result into the current place here, we can write this as x power n plus 1 minus 1. What is x? X is 7 by 4. 7 by 4 whole power n plus 1. What is n? N is k minus 1. Carefully write k minus 1 plus 1. N plus 1 minus 1 divided by x minus 1. X is 7 by 4 minus 1. That's all. So geometric series, right? This is a geometric series. Geometric series. This is simplified using this expression. X power n plus 1 minus 1 by x minus 1. It seems x is 7 by 4. So we have 7 by 4 whole power n plus 1. N plus 1 is k minus 1 plus 1 minus 1 divided by x minus 1. X is 7 by 4. 7 by 4 minus 1. Simplifying, write this result further. This is c into. This is 7 power log n base 2. We can interchange, right, this 7 and n, so that we have, this is n power log 7 base 2 multiplied with c plus a n square. Simplifying this place, plus 1 minus 1 cancels. We have the expression 7 by 4 whole power k minus 1 divided by 7 by 4 minus 1. 7 by 4 minus 1 is 7 minus 4 by 4, that is 3 by 4. So writing here the denominator as 3 by 4. Left hand side is t of n. Let's write the simplification in the next page. Left hand side is t of n, that is t of n is equal to c into n power log 7 base 2 c into n power log 7 base 2 plus 3 by 4, right? When 3 by 4 goes to the numerator, 3 by 4 goes to the numerator, it becomes 4 by 3 multiplied with a n square. So let's write this as 4 by 3 a n square plus 4 by 3 a n square. This is multiplied with 7 by 4 whole power k minus 1. 7 by 4 whole power k, then minus 1. 7 by 4 whole power k minus 1. Now simplifying, right, this k is equal to log n base 2. We can write c into n power log 7 base 2 plus 4 by 3 into a. 4 by 3 is a constant. A is a constant. Right here, a is a constant. 4 by 3 is a constant. Let's write, right, this is a constant. Say, let it be C1. C1 into n square, since C1 is equal to 4 by 3 into E. C1 is a constant that is greater than 0. C1 into n square into, substituting k is equal to log n base 2 7 by 4 whole power log n base 2 minus 1. Simplifying one step further, c into n power log 7 base 2 plus c1 n square. Now 7 by 4 whole power log n base 2. We can interchange the terms n and 7 by 4 for further simplification. Right? So this stage we have n power log 7 by 4 base 2, then minus 1. Simplifying here this stage, c into n power log 7 base 2 plus c1 into n square. This is simplified here, n power log 7 base 2 minus log 4 base 2 minus 1. Writing the simplification further here, this is equal to c into n power log 7 base 2 plus c1 into n square. This is multiplied with these two terms that we can write as n power log 7 base 2 into n power minus log 4 base 2 minus 1. Simplifying one more stage, this is equal to, left hand side is t of n. T of n is equal to c into n power log 7 base 2 c into n power log 7 base 2 plus c1 n square c1 n square is multiplied with n power log 7 base 2 into n power minus log 4 base 2. So here c1 n square, this is multiplied with n power log 7 base 2, n power log 7 base 2 into n power minus log 4 base 2, n power minus log 4 base 2, then minus c1 into n square minus c1 into n square. Now this is n power 2. This is 4 can be written as 2 power 2, so that this is n power minus 2. These two terms are cancelling. Now if we ignore the term minus c1 into n square, now what happens? Left hand side is t of n. T of n is less than or equal to c into n power log 7 base 2, c into n power log 7 base 2 plus c1 into n power log 7 base 2. Because we are ignored, right, minus c1 into n square. Now this is equal to, commonly taking n power log 7 base 2, we have the quantity c plus c1. This is another constant c, c2 into n power log 7 base 2. Now this is in a form of f of n is less than or equal to c into g of n for all n greater than or equal to n0. This is in the form of f of n is less than or equal to c into g of n for all n greater than or equal to n0. This means we can write f of n is equal to big O of g of n. So in the same way here, t of n is less than or equal to c2 into n power log 7 base 2. Therefore, the computing time is given by t of n is equal to big O of n power log 7 base 2. This results in big O of n power 2.81. So we have obtained the solution. The solution is in the form of f of n is less than or equal to c into g of n. F of n is less than or equal to c into g of n for all n greater than or equal to n0. Now f of n is similar to t of n. T of n is less than or equal to some constant into n power log 7 base 2. This is taken as g of n. When f of n is less than or equal to c into f of n is less than or equal to c into g of n, we can write f of n is equal to big O of g of n. Likewise, here t of n is equal to big O of n power log 7 base 2. That means big O of n power 2.81. This is the computational complexity of Strassen matrix multiplication algorithm. And the solution to this recurrence relation, t of n is equal to 7 into t of n by 2 plus a n square, n greater than or equal to 2, and a constant for n is equal to 1 is t of n is equal to a big O of n power 2.81. This computational complexity is compared to the conventional matrix multiplication as big O of n power 3 or divide and conquer based matrix multiplication, big O of n power 3 there. Now big O of n power 2.81, this is many times better than big O of n power 3 for large input sizes. So for large input size or large orders matrix multiplication, Strassen matrix multiplication algorithm reduced the computational complexity. So in this session, we have focused on how to find the solution to the Strassen matrix multiplication algorithm. We have applied the substitution method with the help of the recurrence relation and determination condition. Finally, we have obtained the solution as t of n is equal to big O of n power 2.81.